Hi, my name is Thomas Petrick, and this is Lab 4, the Physics of Extreme Sports with Ropes. For the introduction to this lab, we're going to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We're supposed to analyze the energies of the real-world example and compare it to a computational model representing an ideal situation. Using Tracker, we will find the positional data for the real-world example, and we'll use GlowScript to compare the ideal and real-world models. For the physics principles, we start with Newton's second law, which is simply F equals ma. However, we get a deviation of this with Vf equals Vi plus F net over m times delta t, and the final position is equal to initial position plus velocity times delta t. These equations we used a lot in our previous labs. In this lab, there's a lot of different energy principles, so we know delta E is equal to 0, and the total is the kinetic energy plus the potential energy of gravity plus the potential energy of the spring is equal to delta E. We know the kinetic energy is equal to 1/2 mv squared. The potential energy of gravity is equal to mgh. The spring potential energy is 1/2 kx squared, where x is L minus L0. Lastly, the weight force and the spring force are negative k times L minus L0 times L hat, and the weight force is negative mg j hat. This is the tracker software. First, I created a reference to the length of the system, which was 0.7 meters. Then, as you can see at every frame, I plotted the center of mass of the spring mass system. You can see in the top right that it plots the graph, and at the bottom right you can see the time, the x, and the y position coordinates. After that, I created a CSV file to implement my data into my code. For part 1 of the code, the beginning of the part was all given. However, the part that I edited was the ball's mass, position, and velocity. The mass was given in the video, and the position I found using my tracker software, and the velocity is 0 since it started from rest. This is the most important part of the code. We know that g is equal to 9.8, which is given. To solve for the spring constant, we use the equation 4 pi squared times m over t squared, where t is the period of oscillation, and that's how I got 6.96. L0 is equal to 0.133. I got that from my video analysis, and the rest is given in the physics principles. On line 87, 88, and 89, again, we use the physics principles spoken about earlier in this video. Once we get to the while loop, we solve for the force of gravity, the force of the spring, and the net force, which is just the force of gravity plus the force of the spring. Again, these were all in the physics principles at the beginning of the video. In 108 and 110, we use Newton's second law. And in 113, 114, 115, and 116, we're using another part that we got from the physics principles earlier in this video. In 121, we use the same exact equations that we used earlier in the code. The last part of the code is all given equations that we had in our physics principles, such as E is equal to kinetic energy plus the potential energy of gravity plus the potential energy of the spring, and we know that delta E is equal to 0. The rest is just plotting the points, which is all given code from EDX. When I run the code, as you can see, there's two graphs, the change in energy versus time and the position versus time. The yellow is the total energy, and the green, the red, and the blue are the three energies that add up to 0. So as you can see, this is how my CSV file showed the energies. However, my position versus time data is very skewed, as they're supposed to be similar, the computational model versus the real world example. However, they're very, very different. For the first what does it mean question, as you can see, the energy principle is satisfied because the delta E is always equal to 0, the yellow line. So when one energy increases, the other decreases so that the total energy is equal to 0 throughout the entire model. The second what does it mean question asked, using the data you obtained in Tracker, make two separate estimates of oscillation periods, first by estimating the period of oscillation from the x position, and second by estimating the period of oscillation from the y position, and compare the two estimates and discuss. Therefore, looking at my thing, I had 6 oscillation periods for the x and the y. So I took the final y time and the initial y time for the oscillations and divided it by the amount of periods to get 1.234 seconds per period. And for the x, I did the same exact thing, however, I got 1.377 seconds per period. This means that the y is oscillating faster than in the x. Therefore, in conclusion, the computational model and the real-world model were very different. However, we did still conclude that the total energy change in the system was 0, and that the law of conservation of energy was satisfied. Also, the Newton's second law holds. However, there are lots of sources of error that could have caused the difference in the models, such as the center of mass could have been misplaced, or the calibration stick could have been inaccurate, or we could have measured the spring stiffness or even the relaxed length of the spring wrong, which would have caused a huge deviation in the data for the real-world model on tracker.